In the winter of 1943, as the machinery of global conflict reached its most perilous tempo, a quiet but extraordinary engineering race unfolded behind sealed factory doors and heavily guarded research rooms. Across Allied command posts, whispered memos referenced an emerging breakthrough, an innovation said to offer unprecedented strategic advantage, though few dared to commit its details to paper. The world saw only the movements of armies, but deep within America's industrial corridors, a small cadre of engineers, draftsmen, and metallurgists labored with a clear purpose: to deliver a weapon of efficiency, accuracy, and reliability unlike anything fielded before. The effort began far from the front, in a converted manufacturing complex where the rhythmic clatter of punch presses and precision lathes became the soundtrack of a wartime renaissance. Supervisors walked the lines with clipped urgency, checking gauges, tolerances, and output charts that reflected both pressure and promise. The project demanded secrecy so complete that even seasoned workers confessed they could not fully discern the nature of the device taking shape. Its parts arrived in sealed crates. Its blueprints bore alphanumeric codes instead of names. Yet everyone sensed the same truth: something consequential was being born here. Reports from the European theater intensified the urgency. Engineers studied fragments recovered from battlefields, twisted metal, stressed bearings, ruptured housings, each one a silent testament to the limits of existing equipment. These failures fueled determination, for every flaw cataloged represented an opportunity for advancement. The wartime environment, harsh as it was, accelerated invention by necessity. Materials once considered experimental now moved into production lines. Processes once deemed too complex became essential. The 1943 project absorbed these lessons, assembling them into a single ambitious direction, defined not by chance, but by disciplined engineering resolve. At the heart of the breakthrough was a principle that had long challenged wartime designers: how to produce greater power with reduced bulk and improved consistency without sacrificing durability. Metallurgists refined alloys capable of withstanding punishing cycles, while design teams pushed tolerances to levels once considered unattainable. Hour after hour, the factory hummed with the cadence of innovation, its workers driving forward with the quiet pride of those who understood the stakes. In these halls, the shapes of war were changing, subtle at first, then profound, as 1943 became the year when theory finally met mastery. By early spring of 1943, the Breakthrough Project entered a more guarded phase, overseen by a select committee whose members represented the most disciplined scientific minds of the wartime American effort. Their meetings were held inside a reinforced briefing chamber, where thick blackout curtains muted the afternoon sun, and a single overhead lamp cast deliberate clarity upon each document reviewed. These men and women examined performance charts line by line, comparing thermal tolerances, rotational stability, and stress distribution models that hinted at the remarkable capabilities taking shape. Every figure was weighed against battlefield necessity, for the front dictated the project's pace. The committee's debates were formal yet intense. Metallurgical representatives argued for newly developed alloys capable of enduring prolonged cycles under harsh conditions, while mechanical specialists insisted on testing revised bearing assemblies that promised smoother operation. A separate subgroup focused solely on harmonizing production efficiency with reliability, recognizing that the device's value hinged not merely upon performance, but upon the ability to manufacture it at scale without compromising precision. The tension between innovation and practicality became a recurring theme,
though the group's shared commitment ensured the discussions never drifted from their paramount objective: dependable superiority. Periodic reports arrived from field observers stationed near active sectors of the European front. These correspondences, often written hurriedly in cramped script, described situations in which existing equipment lagged behind evolving combat demands. The committee studied each account carefully, marking margins with fountain pens as they identified trends of mechanical fatigue, alignment failures, and power inconsistencies. These lessons from the battlefield shaped refinements at the drafting tables, ensuring that the 1943 project did not develop in isolation, but in direct conversation with the realities of modern warfare. Every improvement served a soldier they might never meet. Despite the secrecy, the sense of momentum within the committee grew unmistakable. Observers noted how simulations increasingly matched the desired thresholds, while preliminary bench tests reported encouraging stability. Yet the group maintained its disciplined restraint, recognizing that early success required verification through exhaustive scrutiny. They ordered additional trials, recalibrated instruments, and secured fresh material shipments to eliminate doubt. In doing so, they preserved the scientific rigor that defined the wartime engineering spirit. The committee knew the device's promise was significant, but its reliability would determine whether it became a footnote or a turning point in 1943.
Inside the refinement laboratories, where the faint scent of machine oil mixed with warm tungsten filaments, the engineering teams advanced into the most demanding phase of the 1943 project. Row after row of calibrated instruments lined the benches, each device arranged with the orderliness expected of wartime research. Draftsmen updated schematics with meticulous strokes, translating observations into measurements that guided every alteration. Oscilloscopes traced delicate patterns across green-tinted paper rolls, revealing fluctuations that required correcting. This was the realm where speculation ended and certainty began, for each adjustment carried consequences that would echo across future battlefields. The first battery of precision trials commenced shortly after dawn, when the machinery's internal temperature remained stable and test readings could be captured without interference. Specialists monitored rotational harmonics through heavy headphones, listening for irregularities that betrayed structural imbalance. Others studied heat distribution across the alloy surfaces, measuring expansion rates with dial indicators to ensure compliance with the intended tolerances. The device's early performance demonstrated promise, though subtle deviations revealed opportunities for improvement. Rather than discouraging the team, these imperfections fortified their resolve, reminding them that refined engineering emerged not from simplicity, but from disciplined perseverance. A separate chamber housed durability tests where components endured repeated cycles of pressure, torque, and vibration designed to replicate the punishing conditions of active service. Technicians logged each trial in bound ledgers, recording data with precise handwriting that conveyed both formality and pride. When fatigue lines appeared on a prototype's casing, metallurgists gathered around the specimen to examine the cause. The failure, though expected, became the foundation of a new redesign. In this environment, setbacks were not obstacles, but essential guideposts, directing the engineers toward the resilient configuration required for operational reliability. As days turned into weeks, the laboratory's rhythm became a testament to wartime discipline. Morning calibration, midday adjustments, evening retrospectives, each cycle repeated with unwavering consistency.
Supervisors held nightly briefings beneath lamp-lit diagrams, reviewing the day's findings and approving refined modifications for the next experimental iteration. Though the device remained incomplete, its form grew steadily clearer, shaped by collective determination and technical rigor. The engineers understood that their work operated behind closed doors, yet its impact would extend far beyond the laboratory walls, influencing the very direction of the conflict unfolding overseas. By mid-1943, the project advanced into a new chapter as the first operational prototypes emerged from the assembly benches. These early units were handled with the formality reserved for sensitive materiel. Their polished casings reflected the pale light of the test hangar. Engineers moved carefully around them, consulting schematic binders and measurement charts before authorizing activation. The goal of this phase was simple yet formidable: determine how the device performed when subjected to simulations approximating the unpredictable conditions of wartime deployment. Every switch, indicator, and mechanical response offered clues about the device's readiness for broader trials. Simulations began within an expansive chamber lined with reinforced panels and outfitted with equipment designed to replicate environmental stresses encountered near the front. Temperature shifts were introduced gradually, allowing examiners to study contraction and expansion behavior. Mechanical vibrations were applied through controlled surges, mimicking the tremors of transport over uneven terrain. Operators monitored the prototype's internal readings through analog gauges, watching for deviations that indicated instability. Though a handful of fluctuations appeared during the initial sequence, the overall consistency impressed even the more conservative evaluators. The promise of 1943's breakthrough grew increasingly tangible. During the second phase of simulation, technicians assessed how the device responded to rapid cycle operation. A timed sequence triggered repeated activations, pushing its mechanisms to sustain output with minimal decline. Observers charted performance curves, noting that the refined alloys maintained structural integrity even under heightened thermal and mechanical loads. Occasional recalibrations were conducted by sliding open small access panels, allowing precise adjustments without disrupting the broader test. The prototype demonstrated a level of endurance previously unattainable with existing equipment, hinting that the engineering team's painstaking efforts were nearing fruition. Even with encouraging results, the team maintained vigilant discipline. Daily debriefings convened in a modest briefing room adjacent to the testing chamber, where officers and engineers compared observation logs and drafted amendments to the protocols. The discussion remained measured but hopeful, shaped by an awareness that the project stood at a threshold. Should the prototype withstand the upcoming advanced trials, it would transition toward limited field evaluation, an honor reserved only for inventions deemed essential to national security. The year 1943, already marked by shifting tides in the war, now carried the weight of a technological turning point.
The success of the prototype trials prompted officials to schedule a classified demonstration before a select assembly of military command. The event took place in a restricted proving ground, encircled by patrol units and guarded checkpoints, ensuring no unauthorized observer could approach. Rows of wooden observation benches faced a cleared testing field where the device, mounted upon a stabilized platform, awaited activation. Officers from various branches, their uniforms pressed with wartime precision, reviewed briefing folders containing sanitized performance summaries. Although they had read the reports, many understood that only first-hand demonstration could reveal the device's true significance. When the demonstration commenced, the atmosphere settled into disciplined silence. Technicians moved with deliberate coordination, initiating sequences they had rehearsed countless times. Analog dials illuminated with steady motion as the device engaged, its mechanisms cycling with a consistency that drew attentive glances from the officers. The demonstration emphasized reliability under fluctuating load, showcasing the meticulous engineering that defined the project's philosophy. Instead of dramatic spectacle, the display offered something far more meaningful to military observers: unwavering stability. It was this predictability, quiet, controlled, and exact, that commanded respect in an era defined by operational uncertainty. A series of controlled stress evaluations followed, replicating field conditions that pushed equipment beyond ordinary service expectations. Dust generators released fine particulates into the air, while heat lamps mimicked elevated temperatures encountered in foreign theaters. Throughout these challenges, the device continued to perform within the acceptable range, prompting cautious yet unmistakable nods from command representatives. They conferred in low tones, comparing the prototype's readings to existing wartime equipment. The contrast was unmistakable. The 1943 breakthrough did not merely represent incremental improvement, it signaled a disciplined leap forward in the nation's technical and industrial capability. Once the final sequence concluded, officials gathered within a temporary command tent to conduct their formal assessment. Reports were reviewed, questions posed, and recommendations drafted with characteristic military precision. Although the committee refrained from making public declarations, the tone of their deliberations suggested genuine approval. Several officers remarked upon the device's potential to enhance efficiency across multiple fronts, provided production capacity could meet operational demand. When the meeting adjourned, the engineering teams understood that a decisive milestone had been reached. Their creation, forged in secrecy and refined through rigorous discipline, now stood poised for broader wartime application.
Following the classified demonstration, the challenge shifted from innovation to production, a transition as formidable as the engineering itself. The War Production Board authorized a dedicated manufacturing program, assigning the project to a consortium of facilities chosen for their precision capabilities and disciplined output histories. Inside these plants, foremen reorganized assembly lines to accommodate the device's specialized components, many of which required tolerances finer than those of standard wartime equipment. Crates of newly forged alloys arrived daily, each shipment accompanied by detailed certification sheets confirming structural integrity. The factory floors prepared to translate prototype ingenuity into dependable, repeatable manufacture. Training sessions began immediately for the workers entrusted with assembling the device. In classrooms lit by overhead fluorescents and lined with chalk diagrams, instructors explained the significance of each component, emphasizing how minor deviations could compromise battlefield performance. Assemblers practiced delicate procedures using scaled models before handling operational parts, ensuring they could maintain the consistency demanded by the project. Inspection teams, equipped with micrometers and dial gauges, stood ready to evaluate every unit emerging from the line. Their responsibilities were clear: uphold the exacting standards that distinguished the 1943 breakthrough from commonplace machinery. As production ramped up, managers coordinated closely with logistics officers to secure uninterrupted access to critical materials. Shipping timetables were synchronized with factory schedules, minimizing delays that could hinder output. Meanwhile, quality control stations ran endurance tests on randomly selected units, subjecting them to heat, vibration, and stress cycles to ensure continued conformity to design specifications. Reports from these stations were forwarded nightly to a centralized oversight committee, whose members analyzed trends and recommended procedural refinements. It was a system built not only for efficiency but for resilience, recognizing that wartime manufacturing demanded both speed and uncompromising precision. Gradually, the first mass-produced units began rolling off the lines in uniformly packed wooden crates stamped with classification markings. Workers paused briefly to observe these shipments, aware that each crate represented months of quiet labor and steadfast discipline. The device, once confined to laboratory benches and controlled simulations, now entered the vast supply chain that sustained the front. Though few outside the project understood its purpose, those involved sensed that their efforts were contributing to a turning point. In 1943, industry and ingenuity had become inseparable allies, forging a technological response to the demands of global conflict.
As summer approached, the first shipment of fully approved units departed from the manufacturing depots under strict escort. Transport convoys carried the crates across rail networks woven deep into the wartime supply chain, moving steadily toward ports where outbound vessels awaited departure. Upon arrival in the European theater, the devices were issued to select field units, chosen for their disciplined operational records. Officers received sealed briefing packets detailing authorized procedures, maintenance protocols, and observation logs. Their task was clear: determine how the 1943 engineering breakthrough performed not in simulations or controlled tests, but amid the uncertainties of active combat. Initial reports reached the Oversight Committee in carefully coded transmissions. The tone of these early accounts was restrained yet promising. Field operators noted that the device maintained reliable performance even during prolonged engagements, demonstrating stability superior to previously issued equipment. Mechanical fatigue appeared significantly reduced, and several units reported consistent output under conditions that typically strained conventional systems. Though the reports avoided any celebratory language, an expected formality in wartime communications, the underlying message was unmistakable. The engineering team's meticulous labor had translated into tangible advantage on ground where margins often separated success from setback. As weeks progressed, additional documentation arrived from scattered operational sectors. Certain divisions described how the device sustained efficiency despite exposure to dust, moisture, and abrupt temperature shifts. Technicians praised the durability of the refined alloy assemblies, remarking that maintenance intervals extended beyond the expected thresholds. Commanders, adhering to protocol, submitted detailed performance charts comparing the new equipment with older models still in circulation. These comparisons showed a pattern of market improvement, reinforcing the belief that the 1943 breakthrough represented more than incremental progress. It introduced a dependable solution to long-standing mechanical challenges.
Yet, even with encouraging results, the military maintained measured caution. A dedicated analysis board reviewed every incoming transmission, evaluating patterns, potential vulnerabilities, and recommendations for further refinement. Engineers at the home facilities incorporated these findings into ongoing adjustments, mindful that real-world use offered insights unattainable through laboratory methods. The tone across all departments remained one of disciplined optimism, shaped by equal parts pride and responsibility. For the first time, the device's influence extended visibly beyond testing grounds, entering a domain where its performance stood to shape the broader trajectory of the 1943 campaign.
By the close of 1943, the device had transitioned from a confidential experiment into a dependable asset woven quietly into the fabric of wartime operations. Though its existence never appeared in public dispatches, officers and technicians who worked with the equipment recognized its significance. They witnessed how its stability reduced failures, preserved momentum during demanding engagements, and alleviated the mechanical strains that once complicated field strategies. Within command circles, internal memoranda reflected a marked shift. Confidence in the new technology grew steadily, influencing logistical planning and reinforcing the belief that disciplined engineering could reshape the course of the conflict. Within domestic research facilities, the project's success fueled broader ambition. Teams who once labored in cautious secrecy now applied their refined methods to auxiliary programs, confident that rigorous procedure and meticulous craftsmanship could yield further advantage. The device became a benchmark for wartime engineering, an example cited in closed-door briefings whenever reliability and efficiency were demanded simultaneously. It served as evidence that American industry, when aligned with scientific rigor and national purpose, could produce innovations that met the extraordinary pressures of global conflict. In laboratories and drafting rooms, its influence echoed as a quiet but enduring standard. After the war, fragments of the 1943 project resurfaced in declassified reports, allowing historians to piece together the scope of its impact. Analysts noted how its mechanisms informed later generations of equipment, particularly those requiring stability under fluctuating loads. Engineers who contributed to the original program went on to shape peacetime industries, carrying with them lessons forged in the intense crucible of wartime innovation. Though seldom acknowledged by name, the breakthrough's design principles lived on, demonstrating how disciplined pursuit of precision advanced both immediate military goals and the broader trajectory of mid-century engineering. For those who had participated directly, the device was remembered not merely as a technical achievement, but as a symbol of cooperation during a moment when unity was indispensable. Metallurgists, draftsmen, machinists, and field operators each played a role, contributing fragments of expertise that, when combined, created a tool worthy of the nation's trust. Their work embodied the spirit of 1943, steadfast, purposeful, and exact. In the decades that followed, the project's legacy endured as a quiet testament to what disciplined minds could accomplish when confronted with the urgent demands of history.